Summer 1940. Two identical Spitfires. Same engine, same pilot. First one takes 11 minutes to reach 20,000 feet. Second one does it in just 7 minutes. The only difference? 3 aluminum blades that everyone said would never work. This is how one engineer's impossible idea changed World War II. Before you watch full story, comment below from which country are you watching. Don't forget to subscribe for more amazing stories. Summer 1940, Royal Air Force Hornchurch Airfield, Essex, England. Two identical Supermarine Spitfires sat side by side on the concrete runway. They looked exactly the same from the outside. Same sleek design. Same powerful Merlin engine sitting under the nose. Same 8 machine guns in the wings. Even the same experienced pilot strapped into the cockpit, ready to fly. Squadron leader Desmond Cook climbed into the first aircraft and started the engine. The Merlin roared to life with its distinctive sound that every RAF pilot knew by heart. Cook released the brakes and pushed the throttle forward. The Spitfire rolled down the runway, gathering speed. It needed 320 yards of concrete before the wheels finally lifted off the ground and the aircraft climbed into the English sky. Cook pointed the nose upward and began climbing toward 20,000 feet, the altitude where RAF fighters would soon be battling German bombers over Britain. The altimeter needle slowly wound upward as the Spitfire climbed. 5,000 feet. 10,000 feet. 15,000 feet. Finally, at 20,000 feet, Cook checked his stopwatch. The climb had taken 11 minutes and 8 seconds. He continued climbing higher, pushing the Spitfire toward its maximum altitude. The air grew thinner. The engine worked harder to breathe in the thin atmosphere. At 32,000 feet, the aircraft simply could not climb any higher. This was its service ceiling, the maximum height where the engine could still produce enough power to keep flying. Cook brought the Spitfire back down and landed. 20 minutes later, he climbed into the second Spitfire. From the outside, it looked identical to the first one. Same airframe. Same engine. Same guns. Same everything. But this time, something was different. Cook started the engine and released the brakes. The Spitfire rolled forward and accelerated down the runway. But this time, it lifted off in just 225 yards. Nearly 100 yards shorter than the first aircraft. The real surprise came during the climb. Cook pushed the throttle to maximum power and pointed the nose skyward. The altimeter needle wound upward faster than before. Much faster. At 20,000 feet, Cook glanced at his stopwatch in disbelief. 7 minutes and 42 seconds. Almost 4 full minutes faster than the identical aircraft he had just flown. But Cook did not stop climbing. He kept going higher. 25,000 feet. 30,000 feet. 35,000 feet. The Spitfire kept climbing with authority that seemed impossible. At 39,000 feet, where the air was so thin that his breath frosted inside the cockpit despite the summer heat on the ground below, the aircraft finally reached its limit. Same plane. Same engine. Same war hanging in the balance over England. The difference between victory and defeat in the Battle of Britain would come down to 3 spinning aluminum blades that aviation experts across America had dismissed as impossibly complex and unreliable. This was Frank Caldwell's impossible propeller design. The one that would eventually make American bombers fly 100 miles per hour faster and give RAF fighters the performance they desperately needed to survive. But the story of how one stubborn engineer's calculations defeated an entire industry's assumptions begins 8 years earlier, in a factory where absolutely everyone said his idea would never work in the real world. Frank Walker Caldwell stood in the test facility of Hamilton Standard Propeller Corporation in East Hartford, Connecticut on a cold February morning in 1932. He was 43 years old, a mechanical engineer who had graduated from the prestigious Massachusetts Institute of Technology. He had the methodical, careful personality of a man who trusted mathematics and data over personal opinions and conventional wisdom. Wire-rimmed glasses sat precisely on his nose. A clipboard was never far from his calloused hands, always filled with notes and calculations. Behind him in the test facility, mounted securely on a massive test stand that shook and vibrated with mechanical fury, spun a gleaming metal propeller unlike anything else in aviation at that time. 3 polished aluminum blades rotated at 2,400 revolutions per minute. But these were not ordinary propeller blades. They could change their angle while spinning at full speed, adjusting automatically to whatever the aircraft needed at any given moment during flight. The telephone call that would change everything in aviation had come just 3 days earlier from Boeing Field in Seattle, Washington. The Boeing Model 247, America's revolutionary new airliner that was supposed to transform passenger travel, sat stranded and useless at Denver Municipal Airport like a racehorse with broken legs. At an altitude of 5,280 feet above sea level, this twin-engine marvel that was designed to fly passengers coast to coast in record-breaking time could barely climb over the Rocky Mountains that stood in its way. The problem was simple but devastating. 2 wooden propeller blades were fixed at a single pitch angle that had been carefully optimized for one specific flight condition. This meant the aircraft worked reasonably well under those exact conditions but performed terribly everywhere else. It was like driving a car that was permanently stuck in third gear. It might work fine on flat highways at moderate speed. But try to climb a steep hill or accelerate quickly from a stop, and you would discover that third gear was completely wrong for those situations. You needed low gear for climbing and high gear for cruising, but this aircraft could not change gears at all. Pan American Airways President One Trip had personally delivered an ultimatum to Boeing that very morning. His message was clear and direct: fix this problem immediately, or we are canceling our order and buying aircraft from Douglas instead. The stakes could not possibly be higher for Boeing and the entire American aviation industry. United Airlines had placed orders for 25 Model 247s, representing millions of dollars in contracts. TWA wanted to buy 30 more. But absolutely none of that mattered if the most technically advanced airliner in the entire world could not clear a mountain range that every transcontinental route had to cross. Caldwell had heard all the objections before, many times. Across America's aviation community, from small regional airports to the biggest aircraft manufacturers, the conventional wisdom flowed like unchangeable gospel from hangar to boardroom, from test pilots to company presidents. Variable pitch propellers were a solution desperately looking for a problem that did not really exist. They were too heavy for whatever small performance gain they might provide. They were far too mechanically complex for reliable operation in real-world conditions. They contained too many precision-machined moving parts that had to operate in an extremely hostile environment where oil froze solid at high altitude and constant vibration destroyed delicate mechanisms. The Army Air Corps Engineering Division, the government's official experts on military aviation, had formally classified Caldwell's hydraulic design as mechanically unsound in their official reports. Even Charles Lindbergh himself, aviation's most famous and celebrated voice after his historic solo flight across the Atlantic Ocean, had personally questioned the entire concept during a private meeting at Wright Field the previous autumn. But Frank Caldwell possessed the quiet, unshakable confidence of an engineer who had been proven correct before when everyone else said he was wrong. As the United States government's chief propeller engineer from 1917 all the way to 1928, covering more than a decade of rapid aviation development, he had watched so-called aviation experts strongly resist metal propellers simply because wood was lighter in weight. They had opposed ground-adjustable propellers because they seemed like unnecessary complexity that would only create more problems. Each and every time, Caldwell's experimental data and careful calculations had completely demolished their assumptions and proven them wrong. Each and every time, the aviation industry had eventually followed where his numbers led, though usually slowly and reluctantly. But this time felt fundamentally different in a way that kept Caldwell awake at night. This time, entire careers and major companies hung precariously in the balance. Hamilton Standard had invested absolutely everything the company had in Caldwell's revolutionary design. 800 jobs in East Hartford depended on this working. Manufacturing contracts that stretched all the way from Connecticut to California would disappear if the design failed. The company that had proudly built the propellers for Charles Lindbergh's famous Spirit of St. Louis aircraft might not survive as a business if Caldwell's careful calculations somehow proved wrong in actual operation. His own personal reputation, built methodically over 25 years of serious propeller development work, now rested entirely on 3 spinning aluminum blades and a hydraulic governor system that used engine oil pressure to automatically adjust blade angle based on constantly changing flight conditions. The basic engineering behind Caldwell's design was actually elegant in its fundamental simplicity, even though the precision manufacturing was extremely difficult. During takeoff and initial climb, when maximum engine power was absolutely essential for getting a heavy aircraft off the ground and into the air, the propeller automatically shifted to what engineers call fine pitch. This was exactly like a car's low gear. It allowed the engine to spin faster and generate significantly more thrust when the aircraft needed it most desperately. At cruising altitude, when the aircraft was flying level at constant speed, the system automatically shifted to coarse pitch for maximum speed and best fuel efficiency. This was like a car's high gear, perfect for steady highway driving. If an engine completely failed during flight, which was always a serious emergency, the propeller could feather its blades. This meant rotating them until they were parallel to the airflow, eliminating almost all the drag that would otherwise pull the aircraft into a fatal downward spiral that pilots could not recover from. The mathematical numbers spoke with absolute certainty that could not be argued with. Caldwell's extensive wind tunnel tests conducted at MIT's advanced facilities had scientifically proven that constant speed propellers could increase the rate of climb by a full 40%. They could extend the service ceiling by 7,000 feet, allowing aircraft to fly much higher. They improved fuel efficiency by 15% across all possible flight conditions and regimes. But numbers written in test reports meant absolutely nothing if the aviation industry flat out refused to believe them and continued using old technology instead. The critical breakthrough that changed everything came on February 15, 1933, when United Airlines President Pat Patterson gave Hamilton Standard one final chance to prove their impossible propeller actually worked. Just one test flight. One opportunity to demonstrate that their radical design could solve Boeing's Denver problem. They would install Caldwell's constant-speed propeller on a Boeing 247 and fly it over the exact same Rocky Mountain terrain that had completely grounded an identical aircraft just 2 weeks earlier. Test pilot Eddie Allen, a former Navy aviator with ice water running through his veins and nerves of steel, would put Caldwell's complex theory to the ultimate real-world test in actual flight conditions. Allen started the engines, released the brakes, and began his takeoff roll. The Boeing 247 accelerated down the runway and lifted smoothly into the Colorado sky. He turned toward the mountains and began climbing steadily. The aircraft passed 6,000 feet, the altitude that had completely defeated the fixed-pitch 247 and forced it to turn back. Allen kept climbing. 8,000 feet. Still climbing strong. 10,000 feet. The Continental Divide, the massive spine of the Rocky Mountains, passed below like it was nothing more than a small speed bump on a country road. The constant speed propeller adjusted automatically and continuously to each altitude change, maintaining optimal engine RPM while maximizing available thrust. Where the fixed-pitch aircraft had desperately struggled just to reach 6,000 feet over Denver, the modified 247 achieved a service ceiling of 20,700 feet with power to spare. The cruise speed improvement was equally dramatic and impressive. The aircraft flew 15 miles per hour faster across all altitudes. Fuel efficiency improved by 12% at normal cruise power settings, meaning the aircraft could fly much farther on the same amount of fuel. Patterson received the complete test results by telegram that same evening. The message was short and decisive: constant speed propeller exceeds all performance claims. Recommend immediate adoption for entire United fleet. Orders began pouring into Hamilton Standard's East Hartford facility almost immediately. But as the company ramped up production to meet demand, a much darker reality was emerging on the global stage that would transform everything. In Germany, the Nazi Party had seized complete power. Adolf Hitler spoke openly about German expansion and reversing the Treaty of Versailles. In Japan, aggressive military leaders talked constantly about Pacific expansion and creating a greater East Asia co-prosperity sphere under Japanese control. War clouds were gathering ominously over both Europe and Asia. The propeller technology that had initially been designed purely for airline passenger comfort and commercial efficiency was about to become America's secret weapon in the coming global conflict. The telephone rang in Caldwell's office on a humid May afternoon in 1933. The caller identified himself as Commander John Towers from the United States Navy Department's Bureau of Aeronautics in Washington, D.C. They wanted to discuss military applications. Specifically, they wanted fast fighters that could outclimb and outrun anything the Germans or Japanese were currently building. They needed bombers that could fly higher and faster than enemy interceptors could possibly reach. The age of modern aerial warfare was dawning on the horizon. And Frank Caldwell held the technological key that would eventually unlock complete American air superiority over both Germany and Japan. The telegram arrived at Hamilton Standard on November 13, 1933, bearing official news that would validate everything Frank Caldwell had fought so hard to prove against industry resistance. The National Aeronautic Association announced that Hamilton Standard Propeller Corporation had won the prestigious Collier Trophy, aviation's single highest honor in America, for development of a controllable pitch propeller. The award cited particular credit to Frank W. Caldwell personally. President Franklin Delano Roosevelt would personally congratulate him at a formal White House ceremony in December. Photographers would capture images of Caldwell shaking hands with the President of the United States. But even as these photographs were being taken and published in newspapers across America, the military aviation establishment remained stubbornly skeptical and resistant to change. At Wright Field in Dayton, Ohio, Army test pilots complained bitterly and constantly about the extra mechanical complexity that constant speed propellers introduced into combat aircraft that needed to be simple and reliable. Major Benjamin Kelsey, chief of the Army Air Corps Fighter Projects Office, voiced concerns that echoed loudly through military hangars across the entire country. What happens when that hydraulic system fails over Germany? When oil pressure drops and the propeller locks up? Fixed pitch props don't break down because there's literally nothing to break. Simple is always better in combat. Caldwell's response to military skepticism was characteristically methodical and data-driven. If military aviators demanded absolute proof of reliability under harsh combat conditions, he would give them experimental data that left absolutely no room for doubt whatsoever. Working brutal 18-hour days in Hamilton Standard's expanded test facility, he personally invented what became known throughout the industry as the whirl test. This involved mounting propellers on fixed test stands to carefully measure thrust output, endurance under extended operation, maximum speed capabilities, and structural strength under extreme conditions that significantly exceeded anything aircraft would ever encounter in actual combat operations. The technical breakthrough that made everything possible was actually elegant in its mechanical simplicity, despite requiring precision manufacturing. Caldwell's hydromatic propeller used engine oil pressure to drive a piston that changed the blade angle through a carefully designed system of gears and counterweights. A centrifugal governor, no larger than a coffee can, maintained constant RPM regardless of constantly changing flight conditions by automatically adjusting blade pitch in real time. When the aircraft climbed and air density decreased with altitude, the propeller automatically shifted to fine pitch, aviation's equivalent of low gear, to maintain proper engine RPM and maximize available power output. During cruise flight at constant altitude, the system shifted automatically to coarse pitch for maximum speed and optimal fuel efficiency. If engine RPM climbed too high during a steep dive, the propeller automatically coarsened the pitch to prevent dangerous overspeed damage to the engine. Most revolutionary of all was the feathering capability. If an engine failed completely during flight, oil pressure from the remaining engines could rotate the dead propeller's blades parallel to the airflow, eliminating the massive aerodynamic drag that would otherwise pull a multi-engine aircraft into an uncontrollable spiral toward the ground. For bomber crews flying deep into enemy territory hundreds of miles from safety, this single feature alone could mean the difference between limping home safely on remaining engines or becoming another lost statistic in the casualty reports. The performance improvements were absolutely undeniable when translated into actual combat capability that military planners could understand. A P-51 Mustang fighter equipped with Caldwell's constant-speed propeller versus the exact same aircraft with old-style fixed-pitch blades showed dramatic differences across every single flight regime. Takeoff distance was reduced by 30%, allowing fighters to scramble quickly from shorter airfields located much closer to the front lines. Rate of climb increased by 40%, cutting precious minutes from the time required to reach intercept altitude where enemy bombers would be flying. Service ceiling jumped by 7,000 feet, giving American fighters significant altitude superiority over enemy aircraft. Combat range extended by 200 miles because fuel efficiency improved by 15% across all power settings. But impressive numbers on official test reports meant absolutely nothing if the propellers failed mechanically when pilots needed them most desperately during actual combat. Caldwell's obsession with reliability drove him to test every single component far beyond its design limits. Propeller blades were subjected to loads 50% higher than maximum combat stress. Hydraulic governors operated continuously for 500 hours straight at temperature extremes ranging from 40 degrees below zero to 160 degrees Fahrenheit. Oil seals were tested with various contaminants that simulated combat damage and maintenance neglect. The breakthrough moment that finally convinced military skeptics came during a dramatic demonstration at Selfridge Field in Michigan on March 21, 1934. Two absolutely identical P-26 fighters took off simultaneously from the same runway, one equipped with the standard fixed-pitch propeller, the other with Caldwell's constant speed system. The performance difference was so dramatic and obvious that observing pilots initially suspected the constant speed aircraft must be carrying a more powerful engine. Time to climb to 10,000 feet, 8 minutes 30 seconds for the fixed-pitch fighter. Only 5 minutes 40 seconds for the constant speed version. Maximum speed at 15,000 feet, 187 miles per hour versus 203 miles per hour. Service ceiling, 28,000 feet versus 34,500 feet. Lieutenant Colonel Carl Spaatz, who would later command all American strategic air forces in Europe during World War II, filed an official report that evening recommending immediate adoption of constant-speed propellers for all Army Air Corps fighters and bombers. The performance advantage, he wrote carefully, is so significant that it represents a fundamental shift in combat capability. Any air force equipped with constant-speed propellers will possess decisive superiority over opponents using fixed-pitch systems. As 1934 ended, Hamilton Standard's production lines operated around the clock to meet orders from the Army, Navy, and civilian airlines. While Frank Caldwell refined his propeller designs in Connecticut, European aircraft manufacturers lagged dangerously behind American innovation in this critical technology. In the sprawling Messerschmitt factories outside Augsburg, Germany's most advanced fighter, the Bf 109, still relied on manually adjustable propellers that required pilots to constantly manipulate pitch control levers during combat. This meant taking their hands off the control stick and their attention away from enemy aircraft at the worst possible moments. British Supermarine Spitfires and Hawker Hurricanes used primitive two-position propellers that offered only coarse pitch for high-speed flight or fine pitch for climbing, with no intermediate settings and absolutely no automatic adjustment capability. The deadly consequences of this technological gap became painfully apparent during the first months of war. RAF combat reports from September 1939 painted a grim picture that kept Air Ministry officials awake at night with worry. German Bf 109s consistently outclimbed British fighters above 15,000 feet, where manually adjusted propellers gave Luftwaffe pilots a crucial tactical advantage. RAF bomber crews reported frequently aborting missions when their aircraft simply could not reach sufficient altitude to clear the Alps or avoid German interceptors. Fighter command pilots lost precious seconds during climbs to intercept altitude. Those seconds often meant the difference between engaging enemy bombers before they reached their targets or watching helplessly as German formations disappeared into cloud cover. By June 1940, with German armies advancing rapidly toward the Channel coast and the Luftwaffe preparing for the massive assault on Britain, Fighter Command faced a technological crisis that threatened the outcome of the entire war. Squadron leader Desmond Cook of 65 Squadron at Hornchurch understood better than most what his pilots faced in the coming battle. Having flown Spitfires against German fighters over France, he knew that RAF performance deficits were not matters of pilot skill or basic aircraft design. They were pure engineering problems with clear engineering solutions. Cook did something radical. He bypassed normal military channels and placed a direct telephone call to de Havilland Propellers, the British licensee for Hamilton Standard's constant speed designs. His request was urgent and specific: retrofit his squadron's Spitfires with American-designed propellers immediately, regardless of official approval or normal procedural requirements. The conversion program began within 48 hours, operating under emergency authorization from Air Marshal Dowding himself. De Havilland engineers worked around the clock in requisitioned hangars at Hatfield, modifying Spitfire MKs from obsolete two-position propellers to fully automatic constant speed systems. Each conversion required approximately 8 hours of precision work. This included removing the old propeller hub, installing new hydraulic lines, calibrating the governor system, and conducting ground tests to ensure proper operation. Fighter Command could spare aircraft for only 24-hour periods, creating a difficult logistical nightmare where squadrons operated with reduced strength while their aircraft underwent emergency modifications. The first converted Spitfire rolled out of the Hatfield hangar on June 15, 1940. Squadron leader Cook personally conducted the initial test flight, taking off from the Grass Airfield in aircraft serial number K9847. The improvement was immediately apparent during the takeoff roll. The propeller automatically adjusted to fine pitch, allowing the Merlin engine to develop maximum power while maintaining optimal RPM. Where his previous aircraft had required 320 yards to become airborne, the modified Spitfire lifted off in just 225 yards. But the real revelation came during the climb test that would prove whether this technology could actually save Britain. Cook throttled to maximum continuous power and began his ascent toward 20,000 feet, the altitude where Fighter Command expected to engage German bomber formations. The constant speed propeller adjusted continuously as air density decreased, maintaining engine RPM while automatically optimizing blade angle for maximum thrust at each altitude. At 5,000 feet, 10,000, 15,000, the Spitfire climbed with authority that Cook had never experienced in 3 years of flying the type. At 20,000 feet, Cook glanced at his stopwatch, 7 minutes 42 seconds. Nearly 4 full minutes faster than his previous best time in an identical aircraft. Cook continued climbing, watching his altimeter register heights that would have been completely impossible with the old propeller. 35,000 feet. 37,000 feet. At 39,000 feet, where the air was so thin that his breath frosted inside the cockpit despite summer temperatures at ground level, the Spitfire finally reached its performance ceiling. The tactical implications were absolutely staggering. Fighter Command had been planning defensive tactics based on aircraft that struggled to reach 32,000 feet and required over 11 minutes to climb to intercept altitude. Suddenly, RAF fighters could operate 7,000 feet higher and reach fighting altitude in 2/3 the time. German bomber formations flying at 25,000 feet, previously safe from effective interception, now faced Spitfires attacking from above with energy advantage. Cook landed at Hornchurch and immediately telephoned Fighter Command headquarters. His report was terse and urgent: the Spitfire is now an airplane. Request immediate conversion of entire squadron. Within 72 hours, all 12 operational Spitfires of 65 Squadron had been retrofitted with constant speed propellers. The pilots' reactions ranged from amazement to complete disbelief as they discovered aircraft performance they had never imagined possible. Flight Lieutenant Brian Lane, a veteran of the French campaign, described the transformation in his personal combat diary: "It's as if someone replaced our engines with twice the power. We can climb with the 109s now. Match them altitude for altitude. For the first time since this war began, we're not fighting at a disadvantage." Similar conversions began immediately across Fighter Command, with de Havilland engineers working grueling 18-hour shifts to retrofit Spitfires and Hurricanes before the German assault began. By September 1940, 90% of RAF fighters carried constant-speed propellers. Combat reports from the early phases of the Battle of Britain documented the dramatic change in tactical capability. RAF climb rate advantage allowed fighter command to reach intercept altitude 2 to 3 minutes faster than German planning estimates. Service ceiling superiority of 4,000 feet above German fighters meant that Spitfires could attack from positions where Messerschmitt pilots could not effectively respond. Most significantly, improved fuel efficiency extended patrol time by 45 minutes, allowing RAF squadrons to maintain standing patrols over German approach routes. Frank Caldwell's impossible propeller had given the RAF the performance margin that would determine whether Britain survived or fell to German invasion.